Okay, this video is going to show how we can quantitatively express the strength of an acid or a base using an equilibrium constant. So, thinking back to, whoops, don't want to go that far. Here we go. Okay, so thinking back to what we did before break, we had done work with the equilibrium constant KEQ. We had done work with the equilibrium constant for concentrations, and we had looked at equilibrium constants for pressures. We had also shown you that the subscript for all of these kind of shows what the equilibrium constant is describing. So what we're actually going to look at in this video is the equilibrium constant for acids, Ka, and the equilibrium constant for bases, Kb, and the relationship between the two. So the first thing we want to look at is weak acids. And you know, because we talked about this an awful lot last semester, that weak acids are only partially ionized or dissociated in solution. So if I have a weak acid, so let's say HA, and the A is just standing for acid or anion, and that weak acid, we can write it two ways. We can write it in aqueous solution with no water, just water understood. And so we'll get proton, and we'll get the conjugate base A minus anion, or we can write it as HA plus water in equilibrium with the hydronium ion plus the conjugate base, which would be A minus. So if we do that, we can write an equilibrium expression for each of these. Okay, so what we want to do, I'm going to shift over to Smart Notebook because I like the, well, I'll finish it here. So we want to write an equilibrium expression for each of these. So if I write it for the first, my Ka is equal to the concentration of my products multiplied together, raised to the power of their coefficients, which they each have coefficient of 1, divided by the concentration of reactants. Now, all of these are in solution, so I'm including them. If I do the same for the second reaction, I'm going to have the hydronium ion, because I'm doing concentrations of products multiplied together, raised to the power of their coefficients. I'm not going to include water because that's a pure liquid, so that's omitted from the expression. And I'm going to have the weak acid reactant in the denominator. If you look, these two are the same thing. The only thing that is different is in this one. The first one, we have the proton. In the second one, we have the hydronium ion. So what we can tell by looking at this is with a weak acid, because they are only partially ionized, that means we only have some products and we have much more of the reactant. If our denominator is larger, then that means we are going to have a Ka that is less than 1. And if it's considerably less than 1, then that's going to be weaker than an acid that has a Ka that's closer than 1 to 1. If we look at our strong acids, like let's consider nitric, and we know that that is going to dissociate completely into our hydrogen ion and our nitrate ion. We have no nitric acid left because it completely ionizes. So that means we have all products. We would have all products and no reactants. So our Ka is going to be much larger than 1. And with strong acids, it's so much larger than 1 that we don't even worry about measuring it. Okay, so now what we want to do, I want to get out of here. And I want to look at how does this look for a base? So I'm going to take a weak base. I don't like the way that the example that we use that just has B representing base, so I'm going to use an actual base. So I'm going to take the weak base, let's do ammonia, and that will be in solution, and it's in liquid water, and that is in equilibrium with the ammonium ion and the hydroxide ion. Okay, so we want to write an equilibrium expression for this. So because it's a base, I'm going to write Kb. I'm going to mention that I know it's a base for a couple reasons. Number one, I've memorized that ammonia is a base, but number two, hydroxide ions are produced in solution. And so if you think of the Arrhenius definition of bases, any substance that produces hydroxide ions in a solution is a base. So I know this is a base, and my B tells me base. So I'm going to do concentration of products raised to the power of their coefficients divided by the concentration of reactants. Water is not included because it's a pure liquid. And so that would be our equilibrium expression for a base. If the base is weak, like ammonia is, then it will have an equilibrium constant that is less than 1. If it is strong, like sodium hydroxide, potassium hydroxide, it will have an equilibrium constant that is greater than 1. So if you think about the language that we used, the vocabulary that we used in the last chapter, with something that is weak, the equilibrium is shifted to the left. So it is reactant favored. With something that's strong, the equilibrium is shifted to the right. It is product favored. And we talked about with strong acids and bases, they completely dissociate. Weak acids and bases, they only partially dissociate. Now, I want to go back to this PowerPoint because I want to show you a table that has Kas and Kbs listed for a variety of substances. So, and you have a table like this in the back of your book. You will be using it frequently. The one for Kas are on page 1115. Kbs are going to be on page 1116. So if you want to look at a whole bunch, look there. So you've got strong acid. Talked about its Kas are too large to measure. Then we've got several weak acids. And if you look at these, all of these Kas are less than 1. If you turn around and you look at the bases, we have hydroxide as our base, which is a strong base. All of these would be weak bases, which I can tell because their equilibrium constants are all less than 1. If you remember what was in the previous video, this is our acid. Its conjugate base, so nitric acid is the strong acid. Its conjugate base is nitrate. Because the acid is strong, the conjugate base would be weaker than water, and we talked about it's so much weaker than water that it's considered neutral, no acid or base properties, and that's what we see here with this Kb. So what else can I do with this table? If I am trying to decide, I've got 2 acids, they're both weak, I want to compare them. I want to see if one of them is stronger than the other. What I can do is I can just look at their Kas. So if I'm looking at, let's say, hydrogen fluoride and acetic acid, I compare their Kas. The Ka for hydrofluoric acid is larger than the Ka for acetic acid, so I know that hydrofluoric acid is a stronger acid than acetic acid. I can do the same thing with bases. What I'm going to do here is I would look at their Kb's, and I could determine which is stronger. So like, let's say I want to look at ammonia and I want to look at carbonate. By looking at their Kb's, carbonate has a larger Kb, so I know carbonate is a stronger base than ammonia. Now, there is a relationship between an acid and its conjugate base, or a base and its conjugate acid. And that relationship is an algebraic expression, so Kw, which is something called the ion product of water, is equal to Ka times Kb. But you need a value for Kw, and that value is 1 times 10 to the negative 14th. So, for instance, let's say I've got HF, and I've got this reaction where I have hydrogen fluoride in equilibrium with H plus and F minus. And I know the Ka of HF. What this equation allows me to do is solve for the Kb of the fluoride ion. And so I would do that by saying, okay, I've got Kw, which is 1 times 10 to the negative 14th. That would be equal to, because this is a conjugate acid-base pair, these two right here, I would take the Ka for HF, which is here, 6.8 times 10 to the negative 4th, times Kb. And then basically I am dividing 1 times 10 to the negative 14th by 6.8 times 10 to the negative 4th. So if I do that, I get, I'm going to maintain sig fig, so I've got 2 in each of these. I get 1.5 times 10 to the negative 11th. It's an equilibrium constant, so it doesn't have units. And if I check, I got it right there. If this math is a bit beyond you right now, don't worry. We will come back and we will talk about it more later.